we're going to talk today a little bit about things that make elements themselves, basically, right? And different things we can calculate using the periodic table and using what we know about elements. So answer this question for me. What is it that makes elements different from each other? Yeah. Good. The number of protons that each element contains. That's what makes an element a complete individual. Right? There could be the same amounts of electrons in two different elements. There could be the same amount of neutrons in two different elements. But if something loses or gains a proton, then now it becomes a completely different element. That's super, super important. So take a look at your periodic table and find the atomic number for boron. What's the atomic number for boron? Yeah, it's 5. Atomic number is the number of protons in the element. Okay, it's usually listed at the top. In our periodic table on the wall, it's actually in the bottom left. On your periodic table, I don't know where it's at. Top left? Top left. Okay, so we know that this number it's called the atomic number, and that's the number of protons. That's super, super important. So circle that, highlight it, whatever it is. But atomic number is the number of protons. Okay, protons only. Number of protons only. Okay, atomic number is equal to the number of protons. This number never, ever, ever changes. Okay? Oops, sorry. This number never, ever changes. It's always the same. Okay? If it does change, that means we're talking about a new element now. Right? If we go from 8 protons to 7, we go from talking about oxygen to nitrogen. Right? So that number never, ever, ever changes. Something else that we can find from the atomic number is the number of electrons. Okay? We can find the number of electrons based on the atomic number because it's the same as long as our element is neutral. Right? If we have a neutral atom, that means that our number of protons or positive charges and our number of electrons or negative charges have to be equal to each other. Right? What is the charge of a neutral atom? What numerical value does neutral get? 0. Good. Right? So positives have to equal negatives. Okay, so it's really, really important that atomic number always tells us protons, but it can also tell us the number of electrons if the atom is neutral. Sometimes it's abbreviated by Z, but that's not something you need to be super concerned about. Okay, sometimes you'll see it abbreviated with a Z. But I usually don't do that. It just might do that in your book. Okay, so atomic number tells us how many protons and how many electrons if the atom is neutral. So tell me, how many protons are in aluminum? Look for aluminum. How many is there? 13. How many electrons are in a neutral bromine atom? How many electrons are in a neutral bromine atom? 35. Good. So you see bromine? Group 17 or group 7? It's got an atomic number of 35. So that means it's got 35 protons. And if it's neutral, that means our element also has 35 electrons. Super important. Okay? Questions about that? Positives have to equal negatives in a neutral atom. All right.
So, the number of protons is the atomic number.
Right.
But it's also a number of electrons.
Right.
Wait, how do we know if it's
That's
another electron?
Isn't it just gonna always be?
As long as the atom does not have a charge, that will be the same number. So if I just say, how many electrons are in calcium? If I just ask you, how many electrons are in calcium? You would say 20 electrons. But if I said, how many electrons is in calcium with a +2 charge? Now no longer 20 electrons. Right? Because it has a charge up here. Well, I'll talk to you about how it affects that. But as long as there's no charge up here, that means that my protons and my electrons have to be equal. Okay? I'll talk to you about how it affects the charge here in just a little bit. But as long as there's no charge listed, the electrons and the protons have to be equal, right? Because that means they are neutral. All right, here we go. Atoms of any given element, right? All atoms of the same element have the same number of protons. Because proton is what makes the element that certain element. Okay? So what that means is that every single zinc, okay, find zinc, number 30, every single atom of zinc that we pull out has to have 30 protons. That's important. Everyone has to have 30 protons. What can change about an element is the number of neutrons. Okay? Each zinc atom has the ability to have different numbers of neutrons. Okay? They can't have different numbers of protons because then they're no longer zinc. But they can have different numbers of neutrons. Tyler, thank you. All right.
Can you say that again?
All zinc atoms, like I'm just using zinc as an example, all zinc atoms have to have the same number of protons. They don't have to have the same number of neutrons.
So the neutrons aren't going to be...
They don't affect anything except the mass of the atom. Right? Neutrons don't affect the charge because they have no charge, and they affect the mass. That's it. Okay? What these are called when we have atoms of different numbers of neutrons, these are called isotopes. Okay? Isotopes, here's our definition. Atoms of the same element with different masses or different numbers of neutrons. Okay? Isotopes are different versions of the same element that have different numbers of neutrons, which means they have different masses. So I'm going to show you an example here of this with hydrogen. Hydrogen has 3 isotopes. Okay, hydrogen has 3 isotopes. And so, if I'm talking about isotopes of hydrogen, how many protons does each of those hydrogen isotopes need to have? How many protons can each of them have? 1. They cannot have more than 1 proton, because if they have more than 1 proton, it's no longer hydrogen. Right? But here's our example for hydrogen. These are 3 different isotopes of hydrogen, and they have different names. That doesn't happen for all of them. I don't know why they have different names, but they do. Regular hydrogen, like we know it, 1 proton, 1 electron. That's what we know about hydrogen, right? It's in group 1, so it's only got 1 electron. And it only has an atomic mass of 1, which means it's got 1 proton. H2 is called deuterium. It has a proton and a neutron. Still hydrogen because of its proton number, right? Its atomic number is still 1, which means it has to be hydrogen. It just weighs a little bit more than the hydrogen that we know. Last one is called tritium. Okay, it's got a proton and 2 neutrons. Still all hydrogen, just different versions of hydrogen. And so these are called isotopes.
Do the tritium and deuterium hydrogens work the same as the regular ones?
Yeah, they do, except they're very much less common. They are, if we pulled out 100, no, let's say 1,000 molecules of hydrogen, maybe 1 would be deuterium and maybe 1 would be tritium. Right? The abundance percentage of them is so low that they don't happen very often. They behave relatively the same, right? Especially because they got the same number of electrons as the other versions of hydrogen.
Since they're so rare, do people ever do experiments with them?
Yeah,
compared to the regular hydrogen?
right. Every once in a while, but it's not something that's studied all that often. Yeah, good question.
So the only way to tell that it's an isotope would be to look at the mass.
Right, exactly. Right. And so when you're identifying isotopes, they might say, we're talking about carbon. Oops, I forgot to put my pencil. They might say, what's the mass of carbon 14? Right? That's saying we're looking at the carbon with a mass of 14 instead of a mass of 12 like we usually have. Does that make sense? So that's a way that they can identify what version of the element that they're talking about. Okay, so usually carbon has an atomic mass of 12, right? We're going to get there. That's what this next slide is about. Usually carbon has 6 protons and 6 neutrons. But this version right here would have 6 protons and 8 neutrons because it has a mass of 14. Okay, but let's get there now. Okay, so we talked about atomic number, which is the number of protons only. Atomic mass is now the number of protons plus neutrons found in the nucleus. Protons plus neutrons. Okay, that's what atomic mass is. You need to know the difference between those two things. Atomic number, atomic mass. Atomic number is protons only. Atomic mass is protons and neutrons. So, let's see here. If I asked for the atomic mass of sulfur, what would you say? Look on your periodic table. Atomic mass of sulfur. What would it be? You can all just say it. What is it? 32. 32.06. We can round that to 32. Okay? Atomic number for sulfur is 16. That means there's 16 protons. And atomic mass is 32. Can you see a way that we could solve for neutrons based on this information? Right? What could we do? Yeah, I could take my atomic mass, which is protons plus neutrons equals atomic mass. If I wanted to find my number of neutrons, wouldn't I just subtract my protons over? And that gives me my number of neutrons. Okay? That's a skill we need to be able to do. Okay? We have to be able to solve for the number of protons, neutrons, and electrons in an atom. And so if I know my atomic mass and I know my protons, I'm always going to be able to solve for my neutrons. Okay, I'm going to put that up here on the next slide. So you can write down this if you want, but we're going to pull it up on the next slide as well. Okay. An isotope is just different versions of an atom. And so if I said, I want to know, okay, let's see this. If I had an isotope, like for example, carbon-14, that tells me that my atomic mass of carbon is 14, not 12, like it is on your periodic table, right? Because 14 is an isotope of carbon. So if I know that carbon always has 6 protons, right, I would take 14 minus 6, and that would tell me in that version of carbon, I have 8 neutrons.
But in is this on the periodic table, the normal version of carbon?
Right, okay, so we're going to talk about that. Anna asked a good question. What is the number that's reported on the periodic table? Is that the most abundant isotope? Or what is it? Right, look at the atomic masses on the periodic table. Are they all whole numbers? No, they're decimals. And so that means what the value is that's reported there is a weighted average of all of the abundant isotopes of that element. And so I'm getting a little ahead of myself. I want to make sure that we have our head wrapped around what it is first before we go there. But basically, the number that's reported there is the weighted average of all of the abundant isotopes. And so if we've got one isotope that's extremely abundant, and some other isotopes that aren't, our value on the periodic table is going to be really close to a whole number, right? Because if we look at oxygen, its value is 15.999. So that means it has one really abundant isotope. Do you know what abundant means? There's lots of it, okay? There's one isotope that is much more common than the rest, and that isotope probably weighs 16, right? Because that's what our weighted average is super close to. And that means there must be another isotope that weighs less than 16, but that's not very abundant. Does that kind of make sense? It's a weighted average of all of those isotopes. Okay, so I'm going to explain that here in a little bit again, but that's a good question. All right, so here we go. To determine protons, neutrons, electrons, we use various numbers. I know that my atomic number always tells me the number of protons and the number of electrons when it... Okay, you already have this stuff written down, so don't feel like you have to write it down again, but I want to review hit the main points again. So, atomic number always tells us protons in an atom. It most of the time tells us electrons, as long as our element is neutral. Now we move on to atomic mass. It tells us protons plus neutrons. Sure.
How do we know if the element is neutral?
Unless you have a charge written in the top right corner, it'd be considered neutral. So if we ever see elements like this, those all have charges, right? But if we just see Ca or O or Li, that means they're neutral. Good question. Okay? So we can assume it's neutral basically unless stated otherwise. All right, atomic mass tells us protons plus neutrons, and so we already talked about this, but to find the number of neutrons, we subtract the atomic number from the atomic mass. All right, we said, I'll just put this up again, atomic mass equals protons plus neutrons. So if I want to find the number of neutrons, I subtract protons, and that would give me the number of neutrons. Okay. So let's try it with an example here with uranium-235. So uranium is number 92. Locate uranium on your periodic table. What does it tell you uranium's average atomic mass is? What's the one that's on your periodic table? 230. What'd you say? 238. But I'm telling you, I want us to look at uranium-235. So that's the isotope I want you to focus on. So you don't use your periodic table except to find the atomic number. So if I want to find all three things here. I want to find protons, neutrons, and electrons for uranium-235. What do I automatically know? I automatically know protons is 92, right? Because I can find that right on the periodic table. Its atomic number is 92. That's how many protons there are. My electrons, since this is a neutral atom, how many electrons do I have? 92. And then how can I find the number of neutrons? Not 238, 235 minus 92. 143. 143 neutrons. Okay? You'll see me abbreviate protons like this. P with a little plus. E with a little minus for electrons. You'll see me do that. N is usually just what I write for. You could write it N0 if you want for neutrons. But usually you'll see me abbreviate protons, neutrons, and electrons that way. That's what that means. Okay? Questions about how we solved that? That's a skill that I need you to have from this section. You have to be able to find protons, neutrons, and electrons.
Do electrons have a negative charge?
Electrons have a negative charge. Right. Okay? Now, we're going to go to what happens when our objects do have a charge. Right? When their elements are not neutral. How do we find things if they're not neutral? All right, so sometimes our elements can have different numbers of electrons than protons. And I worded it that way because the only time we want to change the charge, the only time we should change the charge is by manipulating the number of electrons. Because if we change the protons, what happens? We get a different element, right? It's a different element. So we have to change the number of electrons if we want to change the charge. So these elements, these atoms that have different numbers of protons and electrons are called ions. They're called ions. Have you heard that term before? Ions is any type of atom that has a positive or a negative charge. Okay? Any type of atom that has a charge is called an ion. I showed it a couple times here, but charged atoms or ions, they're just written like this. I'm sorry. They're written O -2 or Ca +2, right? The charge is just written up in the top right. That's what it looks like. Okay? So, if we have a system that has more electrons than protons, if we have an atom that has more electrons than it should, right? It's supposed to have 10, but it has 11. What type of a charge would that result in? A negative charge. That's a little tricky, right? If I've got more electrons than protons, that gives me a negative charge. Something weird happened here. Sorry, let me fix this because something happened weird. There we go. Okay, negative charge is more electrons than protons. And so let's do a quick example of what that might look like. I want to look at the atom chlorine. Chlorine is Cl. How many protons does chlorine have? It has 17 protons. And let's say, for example, our atom has 18 electrons. What charge would that result in? A negative what? How many? -1 charge. So we would write it like this, Cl -1. Okay, Tristan, can you put your computer away for me? Thank you. This would result in a -1 charge. You have to just think about how many we're going to have left over, right? If they're even, we have a neutral charge. If we've got extra electrons, that results in a negative charge. If we have less electrons than protons, what does that result in? A positive charge. Okay, it results in a positive charge. If we've got less electrons than we're supposed to have, that means we have more protons than electrons. We would have a positively charged atom. Okay, so this next one, you don't have to write it down. I just want you to think about this. Okay, if I have lithium with 1 less electron than its proton, what would its charge be? Positive 1, right? You got to keep the number on there. So that would be written lithium plus, right? If there's no number written there, we assume it's a 1. Okay, so lithium plus 1. If I have oxygen with 2 more electrons than protons, what would that be called? Oxygen minus 2. Good. Oxygen minus 2. Okay, those are how we write those types of things. I also left one thing out here. We have names for these types of ions. If we have a negatively charged ion, it's called an anion. And if we have a positively charged ion, it's called a cation. Okay, those are 2 names that you need to know. The way I like to remember it is that the cation has the plus sign right in it. Right? It's positive. Or someone taught me like this. This would be a cation. This would be an anion. Right? Deals with average atomic mass. And that's the value that's reported on your periodic table as atomic mass. Okay? We said that most elements occur as a mixture of isotopes, some with a really abundant isotope and some not. Okay? But most elements occur in nature as a mixture of all of their isotopes. Okay, we know that isotopes are atoms of the same element with different mass. You don't have to write that down again. But the average atomic mass takes into account how much of each isotope is in an average sample. So we called it, again, a weighted average of the atomic masses of an element. Right? That's what the average atomic mass is. Maybe write this too. Average atomic mass, this is what's found on the periodic table. Okay. average atomic mass is what's found on the periodic table. And we said it's a weighted average of everything that occurs in that element, all the different isotopes. So, for example, we talked about hydrogen and its 3 isotopes earlier. Hydrogen, deuterium, and tritium. Right? Do you remember that picture I showed you of all 3 hydrogens? Which hydrogen do you think is the most abundant? Right, we talked about it.
Just
Regular hydrogen, 1 proton. Look at hydrogen's average atomic mass, 1.01. Right, I said if you had 1,000 of them, maybe one would be H2, maybe one would be H3, right? That's why my weighted average is so close to 1, because the percentage of the isotopes is overwhelmingly H1, right? Not H2 or H3. Does that make sense? If we pulled a sample of 1,000 hydrogen atoms, probably 998 would be regular H1. So that's why the weighted average is different, okay? So I'm going to give you an equation that we use for finding average atomic mass. Oh, sorry. Average atomic mass is found by taking the percentage of isotope A times the mass of that isotope, plus the percentage of isotope B times the mass of that, plus the percentage of C times its mass. It can be as many isotopes as we have. So we're going to do a quick example here. Just isotope number 1, isotope number 2, isotope number 3, however many isotopes we have. So we're going to do an example. So here is an example about copper and its isotopes. So in this one, copper has 2 stable isotopes. One of them has a mass of 63 AMU, and one of them has a mass of 65 AMU. Okay, and so it says this isotope is 69.17% of copper atoms, right? If we took out 100 copper atoms, roughly 69 of them would have an atomic mass of 63. If we took out 100, roughly 30 or 31 of them would have an atomic mass of 65. So we want to find what's the weighted average of this sample. And so we're going to use this equation right here. One thing that we have to see is that we don't just take the percentage. We need to convert the percentage to a decimal. Convert the percentage to a decimal. So I'm going to take 0.6917 times 63 plus 0.3083 times 65. Right? Do that multiplication first. Right? Do order of operations correctly, and that would give us our average atomic mass. Okay, so go ahead and run that calculation. So I got roughly 63.62 AMU. Right, roughly 63.62 AMU. On our periodic table, we have it at 63.55. Right, that has to do with just rounding things and different. But essentially, that's how we calculate average atomic mass. The percent times the isotope mass, and then add all those together. But you need to make sure that you convert that percent to a decimal, right? Divide by 100 to put it into a decimal place first. Okay, questions about that? I'm going to have you try the last one here on your own. Try this one on your own. Find the average atomic mass of an element that has the following occurrences. There's 3 different isotopes here, so we'll add those 3 sections together. And then I guess that's what you should come out with, but we'll see if you can get it to come out.